All right, we'll get started. So, glad to be back. 9 hours jet lag. I was in Brussels working on reviewing for the European community for a week solid, grading and marking research proposals. I understand Giuseppe did a good job. So he's introduced you to logic, and I'm going to do a quick recap of what he did, as usual. And if there are any questions, you should stop me. We're going to talk about bottom-up and top-down proof procedures. And we need to know that these are reliable. And by reliable, we mean sound and complete. And what that means is that the proof theory corresponds to the semantic theory. So, I mean, you can do all of this in the semantics. You know, you could find out what's true in all models by just checking all interpretations, seeing which ones are models, checking in which ones the formula you're interested in is true, and is true in all the models. And it logically follows from the theory. And we can do that because these are finite theories, but again, it's guaranteed exponential to do it that way. So we need a more efficient way of doing it. And the more efficient way of doing it is through proof theory. And we can show that these more efficient proof procedures, both bottom-up and top-down, are more efficient than this sort of model checking, doing it in the semantics approach. And yet they're exactly corresponding. Every time you can prove something's true in a theory using some rule of derivation, like bottom-up or top-down, you can show that it's corresponding true in all models, because the proof theory is sound and complete. And that's why it seems like sort of nitty-picky stuff to worry about whether these are sound and complete rules of derivation. They're very, very important because they give you these very powerful, efficient proof theoretic tools, and we have guarantees, theoretical guarantees, that they correspond to truth theory, to the semantic theory. So that's the idea behind this background. And this is like a major achievement of 19th and 20th century mathematics, you know, starting with people like Frege and Russell and Whitehead and quite a few other logicians. This whole idea of using proof theory instead of semantic theory, using sound and completeness and so on. So these are like 2 centuries of mathematics we're going to talk about in 1 or 2 lectures. So we're skipping over a few details, right? But you get what you need to know. Before I go into that, are there any questions? I saw a question over here somewhere. No? Okay, good. Don't hesitate to question. Someone asked me why there were 4 lectures missing in the online videos, and it had me puzzled for a while until I realized that one was Family Day and the other 3 were in Reading Week, so there's a good reason they're blank. I wasn't here, you weren't here, nobody was here. So we're going to delete those from the online video. But in my jet lag state, it took me a while to figure that one out. So don't ask me any really hard questions, okay? Just really easy questions today. Any really easy questions? The midterm's on Wednesday, that's a really easy question. I know the answer to that. And it only goes up to, and I've said this several times in Connect, it only goes up to the strips representation. Nothing after that. Nothing on logic. Nothing on planning to CSP, strips to CSP transformations and so on. That's not on the midterm. It'll be on the final, but it's not on the midterm. Okay? Yeah, question. Yeah. Will the midterm resemble a sample midterm? Yes. It won't be the same, I hope, unless I made a mistake. But it might be worth putting it just in case. Yeah, it will be pretty similar to that. Any other questions? Yeah?
Is forward planning going to be on the midterm?
No. No, that's after, I just did the strips representation. If you look in the Connect, I've said exactly it's in the middle of, I think it's the second lecture on planning, or it's the first lecture, whatever it is. I said it in the Connect. It's exactly when I did strips, the strips representation, and I stopped. Okay? Forward planning came after that. Any other questions? And we're trying, I'm whipping the TAs to get the assignment 2 marked by tomorrow, so you have it before the midterm. not an easy task herding the teenagers, but they're doing their best. So, any other questions? Nope. Okay. So we're talking about logic. We're starting with propositional logic. We're doing propositional definite clause logic, PDCL we call it. It's propositional. There are no variables. There are no quantifiers like for all there exists, etc. There are just propositions. They're either true or false. There's a finite number of them. Okay? And there's a very restricted form for the rules. In general, you can have negation and disjunction and so on in propositional logic, but we restrict the rules, and they're just what we call definite clauses. They on the left-hand side, on the right-hand side of the rule, all the clauses look like Q if P and R and S and W. That's it. You can only have the left-hand implication like that. Q if P and R and S and W. There's no negation in here. There's no disjunction. Okay? I mean, there is implicitly because, that is P or not Q, right? I mean, you know all this from your logic courses. So, but this is the only way you can write these things. You can't write that. We're not allowed to write negation or disjunction in propositional definite clause logic. So they're all positive clauses. They're all just saying if all these conditions are true, then this must be true in any model of this theory. A model is an interpretation in which all of the clauses are true. Okay? So that's the restriction we're going to deal with. And it turns out that's a really intense restriction on full first-order logic with quantifiers and disjunctions and negations and so on and so forth, let alone modal logics and all the second-order logics and all that hairy stuff up there. This is a very, very simple form of logic. But it corresponds, there's a programming language called Prolog, which is based on this representation, right? You may have encountered it. And it was a pretty powerful language, and it had variables, but other than that, it didn't have any more than that. Okay? So in the recap, we're going to talk about soundness and completeness. We're going to talk about bottom-up proof procedure. We'll talk, and in this lecture, I don't think I'll get to top-down proof procedure. I'm pretty sure I won't. We'll do that next time. But I will go over the soundness proof. I think Giuseppe did the soundness proof, and he did not do the completeness proof for bottom-up proof procedure. And I'll give you two proofs for soundness, one by contradiction and one direct proof by induction, just so you get the idea two different ways. And then we'll do completeness, hopefully. So I'll quickly go through this recap. Again, stop me if you've heard this joke. No, stop me if you don't understand anything at all. Here we do. Okay, so recapping soundness and completeness. Just a quick review of propositional logic. So given a domain that can be represented with n propositions, how many interpretations are there? Off the top of your head, you should say instantly 2 to the n. There's a truth table for all the propositions, and every entry in the truth table is an interpretation, right? Very similar to the idea of possible worlds. If I don't tell you anything else about the domain, I don't give you any facts that are true in the domain, you could be in any one of those interpretations. Okay? In general, you're going to be in a single interpretation. The world will be in a single state. Okay? But you don't know which one it is if I don't tell you anything else about the world. Okay? But if I tell you some things are true, like it's raining, it's not raining, it's sunny. It's true that it's sunny today. That's a true fact. So all the interpretations in which it's raining are immediately ruled out, okay? Because they're no longer models of the single fact that it's sunny. Okay? So if you know that some logical formulae are true, that's your knowledge base. Your knowledge base is a set of rules of this form, all positive rules. The body can be empty, in which case you just have a single fact, like Q, it is sunny. I mean, I could have a rule, if it is raining, then the grass is wet. That would be another rule. It isn't relevant in the world today because it's sunny today, right? But if it were raining, that would be a true formula. Okay, so all your formula have to be expressed in that form. That's your knowledge base, is a set of formula. Then you can only be in interpretations in which those formula hold. So what are those formulas called? They're called models, right? It's the definition of a model. It's the interpretations in which all the clauses of a knowledge base are true. So once you know you're in a restricted set of the interpretations, the ones in which your facts about the world are true, then you might want to know what else is true, right? So if I give you this knowledge base, you know, if it is raining, then the grass is wet, and I tell you it is raining, right? Then we also know that in any model of those formulae, the grass is going to be wet. I didn't state it explicitly when I gave you the facts about the world. I just gave you a rule. If it's raining, the grass will be wet, and I gave you the fact that it's raining. Then I'd like to know that the grass is going to be wet in any model of those formulas. So that's what we call a logical consequence. If KB is a set of clauses and G is a conjunction of atoms, G is a logical consequence of the KB, written KB double turnstile. Okay? This is very important. There's a double turnstile there. That's a semantic notion. Okay? Not a proof theoretic notion, but it's a single turnstile. So all this, just read this as G logically follows from the knowledge base. I mean, you can read it as KB semantically entails G. That's a little awkward. So we usually just say G logically is a logical consequence of the knowledge base. Okay? And that's just a definition. That holds, this statement holds if G is true in every model of the knowledge base. And here's some example, right? If we have this knowledge base, H if A is true, and D if C is true, okay? For which G is knowledge base, G logically is a logical consequence of the knowledge base. That should be clear to you from that. Just inspecting that knowledge base, you could run bottom-up consequence finding on that. We know that A must be true, right? And if A must be true, and if A is true, then H is true, therefore H must be true. That's our bottom-up consequence finding algorithm. So it looks like A and H. This doesn't come into play because we don't know C. So therefore we don't know if D is true or not. May or may not be. C could be true, or it could be false. D could be true, or it could be false. If C is true, then D has to be true, right, in any model. But we don't know the status of C, so we only know that A and H are logical consequences of this knowledge base. Okay? So if we know that the knowledge base holds, we're in a model, we can immediately assume not only is A true, but also H must be true because of that rule. Okay, so there's this idea of intended interpretation, right? I mean, that's imposed on by you, the user. You're looking at this theory from the outside, and you're saying, I really want this world to be the case. Okay? So you're choosing the task domain. And that's the interpretation of the symbols the user has in mind. I mean, the computer doesn't know what these symbols mean yet, right? Right. It is raining doesn't have any meaning to the computer. It might as well be Q or P or R or anything else, right? So they have there's no semantics inside the computer yet. So that's imposed on it from outside. Of all the possible interpretations, some of them will be models, and of those models, one of those models will be the intended interpretation. Okay, that's the one you're thinking about. However, the computer or the proof theory can only reason about all the models. Okay, and that's typically what we do. So you tell the system various clauses. You might, if you were running Prolog, you just insert them as clauses. That's the knowledge base, and each clause is true in your intended interpretation. Thus, the intended interpretation is a model. The computer doesn't know the intended interpretation. But if the computer knows in double quotes, scare quotes, knows how to derive what's true in all models, since the intended interpretation is a model, what's true in all models must be true in every single model, therefore it's true in the intended interpretation, right? So because you've got this proof procedure that can derive what's true in all models, you can be sure that it'll be true in your intended interpretation, because the intended interpretation is a model. It's a model because you make sure that the clauses you tell it in the theory are true. right? So that's what this says. You can derive something that's true in all models, and it's true in the intended interpretation. So we want to derive logical consequences. We want to say, given a theory, what are all the logical consequences of that theory? What is true in all models? Okay, so here's a chance for you to use your cards just to check what I just said. So just remember, this is the definition. This, if I ask you define logical consequence, this is what you regurgitate. KB is a set of clauses and G is a conjunction of others. G is a logical consequence of the knowledge base. Written G, KB double turnstile G, where G logically follows from KB. If that's the case, if G is true in every model of the knowledge base. So if this holds, then which of these four possibilities hold? In multiple, maybe more than one answer of these is correct. All right, so is it true that G isn't true in the intended interpretation? Is it true there's at least one model of KB in which G is true? Is it true that G is true in every model of KB? Is it true that G is true in some models of KB, but not necessarily the intended interpretation? Think about it. Look to your neighbors, see what your neighbors got. Double check. Got extra cards if you forgot your cards. Okay, so now that you've had a little chat with your neighbor, possibly, what's your answer? Or your answers? Okay, so I see some good answers. There are actually 3 true answers. The first 3 are all true. All right? The last one is false because G is necessarily true in the intended interpretation because the intended interpretation is always a model, and G is true in all models. If G logically follows from the knowledge base, it's true in all models. So it's true in the intended interpretation. There's at least one model of the knowledge base in which G is true. I mean, that's a kind of tricky one. Maybe there aren't any models of the knowledge base, but there's always at least one model of this kind of knowledge base, as we'll see in a minute. And G is true in every model of the knowledge base. And that's just that's the definition up here. It's written down here, right? It's true in every model. Then there's at least one model in which it's true if there is a model. And it's true in the intended interpretation if the intended interpretation is a model. This last one's false, the red one. Yeah, question?
So like you're saying, presumably the blue one's only true in virtue of the type of logic we're using.
That's correct.
Like in first order logic, you get out an inconsistent knowledge base. So
That's absolutely true. Yeah. Yeah, as I said, this is a bit tricky, the second one. But in this case, we'll see there's always a model for every PDCL theory, every propositional definite clause logic theory. There's always at least one model. So that's a good question. It's a claim. Notice there's always at least one model of any PDCL theory. What is it? You're making a claim. Can you prove that's true? As a theorem. There's always at least one model of any PDCL theory. How do you prove that? What?
all the atoms are true?
Yeah, if all the atoms are true, right? I mean, think about it. For any propositional theory, you have a bunch of atoms. Say there are n of them, right? Then you write down the truth table for those n atoms. There are 2 to the n entries in the truth table. One of those entries says they're all true. Okay? Now look at the clauses. If they're all in this form, which they have to be in the PDCL theory, true and true and true and true and true implies true. This clause will be true. Any clause in this form will be true. Right? So there's always a model for this kind of theory. There's always at least one model. That's an important theorem. As soon as I start adding negation or anything else, I don't even have to go to first order. I can do it in propositional. I could write down a propositional theory, P not P. Right? There's no model for that. If P is true, then this is false. If P is false, then this is false. There's no model in which all these can be true at the same time. But that's not, this KB1 is not DDCL. Because you've got that negation in there. So this is the key, that they're all positive in this form that allows you to deduce this theorem. The interpretation with every atom true is always a model in the simple case because each clause is true in that interpretation. Okay? That should be clear to you now. If it's not clear, you've missed something along the way. So you need to go and read the book, read the last lectures, listen to Giuseppe, listen to me, etc., etc. That should be clear to you now. Okay, so we're still really recapping. We're talking about proofs. And this is the key idea, is that the computer can prove things. Computer can prove theorems. It's thought to be only a human capability, right? But no, you can write mechanical theorem provers, and they've been written for very large theorems. In fact, computers have proved theorems that mathematicians couldn't, human ones. But we're dealing with very simple theorem provers here. What is a proof? We have a technical definition of what a proof is, okay? It's a mechanically derivable demonstration that a formula logically follows from a knowledge base. So you have to start with your knowledge base, and you have to have a syntactic algorithm which just grinds away on the knowledge base until it either shows the theorem's true or it's false, okay? Now for some theories, like some first-order theories, you may be able to prove it's true, you may never be able to prove it's false, but we're not concerned with undecidability for these theories because they're so simple. They're decidable theories. So, definition, derivability with a proof procedure. Given a proof procedure P, KB, single turnstile, subscripted by the proof procedure G means that G can be derived from the knowledge base KB with proof procedure P. So this is just a shorthand. This definition is just, that symbol is a way of writing down this sentence. Okay, and we would usually say that G is derived using P from KB. That's how you'd read that sentence there. Okay? Then we're going to talk about different kinds of proof procedures. Bottom up, top down. We can even do middle out, but we won't in this course, but we'll just do the simple stuff. We want certain properties for these proof procedures because we want to relate back to the semantics, right? The logically followed the notion of double turnstile. So what's the connection between the single turnstile and the double turnstile? And there's two ways you want to go, of course, right? I mean, the easy one is to show that if G is derivable by P from KB, that implies that G is logically follows from the knowledge base. G is a theorem, is a way of saying it. Okay, so that's sound. It means that every time you derive something, it's true in all models. So it's a good use of the word sound, right? It means that you're never going to make a mistake. Everything you prove mechanically, derivably, will be true in all models. Okay? Every atom, so you should not realize that, and remember, every atom G that P derives follows logically from the knowledge base. So this is the derivation, this is the follows logically. And of course, we want to go the other way. We don't want to miss any theorems. Okay, this says everything you can prove is a theorem, but this says every theorem is provable, right? So we want completeness, which goes the other way. If G logically follows from the knowledge base, that implies that G is derivable by P from the knowledge base. So completeness says every atom G that logically follows from the knowledge base is derived by the mechanical procedure P, okay? Which does it without enumerating all interpretations, all models, and so on, doing that incredibly tedious stuff. It just grinds away on the theory itself. It doesn't even look at the interpretations, but if we can prove that P is sound and complete, we've got an ironclad guarantee that we're only going to prove theorems. And that seems like a good thing to have, right? So then we might look, a couple of cases. What about an unsound proof procedure? So U, let's just invent a proof procedure U. It's a really dumb one. U derives every atom from the knowledge base. For any G that appears in the knowledge base, we say that G is derivable from the knowledge base. You know, don't use this at home. It's dangerous. It doesn't work. But you could claim that's a proof. It is a proof procedure. It's unsound, right? Because there are atoms that it derives that do not logically follow from the knowledge base. So if the knowledge base is A if B, you've just got that one rule, then it'll derive both A and B, because they're both mentioned. It's going to derive anything that's mentioned in the theory. So it's going way too far, right? So if it's derivable, it doesn't imply that G logically follows from it, so it's unsound, right? A and B do not logically follow from this knowledge base, because there are interpretations in which it's false. So the proof procedure U is complete. Of course it's complete, because it says every possible atom is a theorem. Well, some of them are theorems and some of them aren't, but you know, it's going too far, but it is complete. So it will not miss any atom, since it derives every possible atom. So we're just giving you extremes here, right? How about incomplete? Well, really incomplete would say nothing follows from the knowledge base. Well, these are just imaginary proof procedures. We're looking at the notion of incompleteness and soundness. So this incomplete procedure, we'll call it I. There's no atom G such that G is derivable. But it is sound. It's so careful it doesn't derive any atoms at all. So every atom it derives, of which there are none, does follow from the knowledge base. It doesn't go overboard and prove theorems that aren't true, because it doesn't prove it doesn't derive anything. Okay, so it's sound, but it's incomplete, because it obviously, any atoms that do logically follow the knowledge base will be missed. So these are the two extremes, and we want to come to the middle and find procedures that are both sound and complete. So I think Giuseppe went over this extensively, the bottom-up proof procedure. You just start by saying there are no consequences of the theory, and then you just keep adding consequences in that you're forced to believe in, right? So if any single atom's in the theory, like if you just have an atom P, then you must put that into your theorem, into your set of consequences, right? So if I have an atom, if I just have that, then obviously the first thing I want to believe is P is always true in any model, right? Because that clause has to be true in every model. So you put those in first, and then you see, have I got all the atoms in the set of consequences? So I build up this set of consequences, and then I see at any stage, do I have all the atoms on the right-hand side of a rule in the set of consequences, and I don't yet have the head? If so, throw the head in, because if these are all forced to be true, then this will have to be forced to be true if this rule is true in every model, right? Which it has to be. Okay, that's all this thing is doing, right? I don't think we need to go over it. Start out with empty. Just select a clause. Doesn't matter what order you select them in. It has this convergence property. It makes no difference, the order of selection here. So it's what we call a don't care non-determinism. Select a clause in the knowledge base such that each of the atoms is in the set of consequences and the head is not. Then add the head to the set of consequences. Keep doing that until no more clauses. There's no clause that has all its atoms in the body in the set of consequences, but it doesn't have its head in yet. Okay, eventually that'll happen. This has to terminate eventually. It's easy to prove. And that's the bottom-up proof procedure. And so we could just run it on this theory. I think Giuseppe did all this, right? This looks familiar. So with this theory here, you start out with the atom E, because that has to be in. And then you say, are there any rules with E on the right-hand side alone? Yes, this one. So that'll force C to be in. And how about, where did I get F from? Down here, probably somewhere, yeah. C will force F to be in, and so on and so forth. Once you get to these atoms, these are the 5 that are forced to be true in this theory. There are no more rules with any subset of these atoms on the right-hand side and doesn't have the head in. So you've reached a fixed point, you've stopped, you're done. These are 5 consequences of the theory that have to be true. So the first thing we wanted to do was to prove that that was sound. And I think Giuseppe also did that. But are there any questions about this? But it's very simple. We're just putting into the consequences things that are forced to be true. They have to be true. If all the clauses are true, so we're working in a model here, we want to know what's true in all models, then obviously any single atom that's in the theory has to be true. But we know more than that has to be true. If any rule has all atoms true on the right-hand side in the body, then ka-chunk, it forces the head into that set of atoms that are forced to be true in all models. Right? So we're collecting up the set of atoms that has to be true. The rest of the atoms in the theory is a finite set of atoms, so we're going to collect the set that is forced to be true. The rest could either be true or false in any model. We don't care. These are true. This is the set that has to be true in every model. Okay? Questions about that? And it's all covered in the book. It's a little strange if you haven't encountered these ideas before, proof theory. So then we want to prove that this is sound. Okay? Remember what soundness is? A proof procedure P is sound if G derivable by P in the knowledge base implies that G is true in all models of the knowledge base. Okay, so we've got a proof theoretic idea here, we've got a model theoretic idea here, right? Or syntactic. So this is syntactic, this is semantic. That's another way of thinking about it. We want to connect the two here. For this particular proof procedure, bottom up, we want to show that it's sound and complete. It's easier to show soundness. I mean, it's almost, how could it not be sound? Because of the way I described it. You take all the true atoms, they're in the set of consequences, and the ka-chunk you add in the ones that are forced to be true as you go along. And that's the set that is logically following from the theory. But we have to prove it formally. So there's the algorithm again. So what do we need to prove to show that BU is sound? If G belongs to C, the set of consequences at the end of the bottom-up procedure, then G is true in all models of the knowledge base. That's just restating, given that the set of atoms derivable by P is the set of atoms that's in the set of consequences C. Okay? So if an atom is in that set of consequences here when this thing stops, then G is forced to be true in all models of the knowledge base. And we're going to prove that two ways. First, we'll do it again by contradiction. I think Giuseppe did it this way last time. And then I'll do a direct proof by induction. Okay, so for soundness, we just restated that. And we'll prove it by contradiction. Consider a G in C there, but suppose it's not the case that G logically follows from the knowledge base. Okay, so this is our hypothesis that we're going to show can't be true, because we'll get a contradiction if we assume that G is derivable from G is derivable from KB, but doesn't logically follow from it. Okay, suppose that's the case, then there must be a first atom, we'll call it H, that's added to C that's not true in every model. So G is not true in every model. It may not be the first atom that we add to C for which that's the case. It may or may not be. But let's H be the first atom added to C that is not true in every model. There must be such an H if this hypothesis is true. And so it's not true in every model. There must be a particular model in which it isn't true. Right? That follows directly. Suppose I is the model of a model of KB in which H isn't true. It's got to be at least one because it's not true in every one. So if that's the case, there must be a clause in the knowledge base of the form H if B1 through Bm. Why is that true? Because H got added. The only way it can get added is if it's at the head of a clause, right? Like that. Each Bi is true in I, because it's true. Each of the Bi's is true in all models. H was the first atom for which it's not true in every model. So Bi's are all true. H is false. As we said here, H is the first atom that's not true in every model, and it's not true in I. So H is false. These are all true. This clause is now false. Right? False if true is a false clause. right? False if true is false, right? Remember that from your implication. So this clause is false in I, right? But I is a model of the knowledge base, right? But it isn't a model. So since that clause is false, it's not a model of the knowledge base. Whereas here, we presume that I is a model of the knowledge base, but now I is not a model. We've got a contradiction. Thus, this cannot be true. No such G exists. It's a fairly simple proof by contradiction. Does that make sense? Get it? You did it before, I think, right? You saw this before for Giuseppe? Vaguely familiar? Thank you. Okay. So that was this is all review. The whole lecture so far has been review, okay? So you should have been able to get all of it. So this is new, I think. We'll give a direct proof by induction of the same theorem that bottom-up procedure is always sound. Okay, here's the inductive proof. We're going to do a familiar induction on the loop. Okay, so what we're going to use is an inductive hypothesis. We'll call it AH. The inductive hypothesis, if G is in C at loop iteration n, then G is true of in all models of the knowledge base. Right? So, this is the base case. The inductive hypothesis holds for n equals 0. For n equals 0, loop iteration, I haven't done any loop iterations, so C is empty, so it holds. Because there's no G in C, so it's true in all models. It's trivially true. Here's the inductive case. If this hypothesis holds for n, then it holds for n plus 1, right? That's what we want to prove. If we can prove this, and we proved it for n equals 0, then it's true for n equal 1, 2, 3, 4, and so on, as long as it goes. And we know this loop will halt, so it's true for any finite n. So it's true when it finishes. Okay, so if the inductive hypothesis holds for n, it holds for n plus 1. In other words, if it holds before a loop iteration, if you do it one more time, it'll hold after the loop iteration. Classic inductive loop proving. So imagine one more iteration of this loop here, selecting a clause H if blah blah in the knowledge base, such that this is true and H is not already there, add it into the clause. Okay? The only new element in C is H, so we only need to prove that H logically follows from the knowledge base. Every other atom in C was in there before the loop iteration, so we don't have to prove it for them. We just have to prove it for the one we just added. Okay? So, how do we do that? These atoms were in C before, right? So by the inductive hypothesis, we know that these logically followed from the knowledge base. Okay, we're assuming this holds for before the loop does this one more iteration. So all of the atoms in there must logically follow from the knowledge base, therefore the conjunction logically follows from the knowledge base. Okay, so we know that. In every model, this body is true, and the rule is true, because that's the definition of a model, right? Thus, in every model, H is true, right? Because we know this is true, and this is true. The only way for this to be true, if the body is true, is for the head to be true. It's the law of truth table for implication, right? Therefore, in every model, H is true. So we're done. We've proven this inductive case, and so we've proven the theorem that if G is derivable bottom-up from KB, that implies that G logically follows from KB. Okay? So you may not grok this theorem the first time through, but if you've done any inductive proofs, and I know you've done them, you can deny it all you like, I know you've done it before, right? Then you should be able to follow this one. And we do it in the book, and I think we do this one in the book. Anyway, this is absolutely clear and easy to follow.
Question.
Question, yeah.
For the last step, do we also mention the case where m equals 0, or do we assume that?
Yeah, if m equals 0, this is trivially the case, right? There's no body, so it's true, and H got added, right? Yeah. Yeah, all of these theorems apply when there's no body, n equals 0, because it's trivially true. Any other question about the proof? Good. So we've done soundness two different ways. Completeness is a little trickier. Okay? So let's do the completeness proof, which goes the other way, right? First, we'll start with this idea of a minimal model, and it's a fairly easy idea to get. These are the atoms that are forced to be true by the bottom-up procedure, the ones that are in this set C. All those atoms have to be true in every model, right? We know that. They're forced to be true. The basic atoms in the theory and then the ones that were forced up by the rules. This is a set of atoms that have to be true. Okay? Now the minimal model we'll define to be the model where all of those atoms are true and all the other atoms are false. By minimal we mean as small as possible. We want the minimum number of things to be true. And you know that the set of atoms in C has to all be true in every model. So you can't get away with making any of them false. So they're forced to be true. And let all the other atoms be false. We'll call that a minimal model. But actually we need to check that that is actually a model. Just by calling it a minimal model doesn't mean it is a model. Okay, so the first thing we need to do is to define this idea of a minimal model. So the minimal model MM is the interpretation in which every element of BU's fixed point C is true. The ones that are forced to be true are true. And every other atom is false. Okay? So we start with C empty in the derivation. We ka-chunk add in all the atoms that are just true because they're just in the theory as rules with no body. And then we add all the other ones that get added, ka-chunk, 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 ka-chunk. Stop, it's finished. There are no more that are forced to be true. Let all those atoms be true, every other atom be false. Let's call that a minimal model. But first we have to make sure that it is a model. Okay? We can't get away with just by calling it a minimal model, assuming it's a model. So we have this little lemma we have to prove that the minimal model is indeed a model. Okay? So by definition, the minimal model is the interpretation in which every element of BU's fixed point C is true and every other element is false. Okay, so, I mean, this is pretty abstract stuff, but it's important. And I realize that it's not easy to grasp the first time through if you're not used to dealing with these things. So don't worry if it doesn't make sense yet. But it is in the book, and it's written out in a lot more words than I'm giving you here. The lecture will be on video. You have my slides, etc., etc. You should go over and over and over until you finally get every theorem and you could prove it yourself. Okay? So again, we're going to start, and the only proof I'll give for this to keep it simple is by contradiction. Okay? So I want to prove that this is the statement of the theorem. A minimal model defined this way is a model. It's actually fairly easy. I mean, intuitively, what else could it be, right? But we have to prove it. Okay, remember what a model is? It's a knowledge-based model with knowledge-based interpretation in which every clause is true. So we'll prove it by contradiction. So we say, well, the theorem's false. Unless so that if the theorem's false, then we get a contradiction, therefore the theorem must be true. Assume by contradiction that the minimal model is not a model of the knowledge base. How could that be true? Well, then there must exist some clause in the knowledge base which is false in the minimal model, because in every model all the clauses are true, so there must be one that's false. That clause must have some form like H if B1 through Bn, with m greater than or equal to 0. Okay? This clause, which we say there must be such a clause if this false hypothesis is true, how could that be false? It could only be false in the minimum model if each BI is true in the minimum model and H is false. The only way an implication can be false is if the body is false and the head, if the body is true and the head is false, right? It's the only way an implication, I mean, this should be second nature to you now. The only way an implication can be false is if the body is true and the head is false. And we want that to be false for this reason, okay? So each of the BIs must be true in the MM and H is false in the MM. Since each of the BIs is true in the minimum model, each BI must be in C as well, because each BI is true in the minimum model. We've said the minimum model is the set of atoms in C, right? So it must be in C. If it were in C, and you have this rule in the knowledge base, then the bottom-up would add H to C, right? So H would be true in the minimal model. But H is false in the minimal model. Uh-oh, but actually, that's a good news. There's a contradiction. H is false in the minimal model, and H is true in the minimal model, if minimal model is not a model. So it has to be a model. We proved the theorem. Contradiction, therefore, minimal model is a model. And again, this is kind of subtle, but every step is precisely correct. This is a very formal technical proof. Bulletproof. Okay? So, now we need to show that the bottom-up procedure is complete. And we're going to base the proof on that lemma. We just proved the lemma. We haven't proved the theorem yet that the proof procedure is complete. A proof procedure is complete if when you, for every theorem, there is a derivation, right? If everything that logically follows from the knowledge base, this thing, implies that G is derived from the knowledge base. Okay, so that means every theorem is provable by the derivation procedure. So, suppose this is the case, right? We've got a theorem. G is true in all models of the knowledge base. G is true in all models of the knowledge base. Okay, let's suppose that's the case. Since G is true in all models of the knowledge base, it must be true in the minimal model. That's what we need the minimal model for. And we know it's a model. So G is true in all models, therefore it must be true in the minimal model. Okay? Since it's true in the minimal model, the only atoms that are true in the minimal model are the ones that were forced to be true by the bottom-up procedure. If it's true in the minimal model, it must be in the set of consequences at the end of the bottom-up procedure. That follows. Thus, KB, bottom-up, derives G. Right? So in other words, if G logically follows from the knowledge base, G is true in all models, therefore it's true in the minimal model, therefore G is in C at the end of the bottom-up procedure. Therefore, it's derived by the bottom-up procedure. We're done. Very straightforward proof. But it was this technical idea of the minimal model which was the key stepping stone to get us to prove that theorem. Okay? So if G logically follows from the knowledge base, G is derivable. So it's sound and complete. We can replace semantic checking for these theories with bottom-up proving. And that's a huge win because bottom-up is much more efficient. It's linear, basically, as opposed to exponential, the semantic checking. Okay, so this is a huge win. We only have to do it once. Thank God you only have to sit through these proofs once. Once you got them, you know, okay, I can now rely on bottom-up derivations, and I can forget about, because it's sound and complete. BU sound, it derives only atoms that logically follow from the knowledge base. It's complete, it derives all atoms that logically follow from the knowledge base. So it has to derive exactly the atoms that logically follow from the knowledge base. And it's efficient. It's linear in the number of clauses in the knowledge base. Each clause is used maximally once by the bottom-up procedure. You never reuse a clause, because once you use a clause, its head goes into C, and you'll never use that clause again. Okay? So, these are your learning goals up to here. You should know all of this by Cole by now. It's not in the midterm, but it will be later. And we'll get to top-down proof procedure on Friday. And I'll see you here on Wednesday. Okay. Cheers.